Good day, everyone. So today we're going to go over sections 11.1 and 11.2. And so we're going to change uh, our focus here to creating a confidence interval for mu and not the population proportion p. So here's an example. Screen time is a serious problem for children. They're sitting around a lot. They're not doing much activity. So the more the screen time, the more the child is at risk for attention problems, anxiety, and depression. So to estimate the daily mean screen time for all 5-year-old Americans, 25 5-year-olds are randomly sampled. The daily mean screen time for the 25 children is 182 minutes with a standard deviation of 28. Create a 90% confidence interval for the daily mean screen time for all 5-year-old Americans. Assume that the daily screen time for 5-year-olds is normal. All right. Got my pen out. So, first of all, why are we making a confidence interval for the population mean mu and not the population proportion p? The reason why is because the underlying variable, the variable that we collect the data on, is quantitative, not categorical. When it's categorical, we look at proportions or percentages. When it's quantitative, we look at averages slash means. So here, screen time is the variable that we collect the data on, and it varies from what? Person to person, right? It varies from person to person. And so that's why we have changed our focus over to mu instead of the population portion p. All right, so now every confidence interval has this form with regards to its formula, point of estimate plus or minus the margin of error. Remember, the margin of error is the critical value times the standard error. And remember when we talked about this a couple of sections ago, that when we're creating a confidence interval for mu, we can't use p hat, right? And we can't even use the standard normal for the probability distribution. Recall that the point estimate for a confidence interval for mu is what? It's x bar, right? It's x bar, so we're not using p hat. And so we should be able to identify x bar in the problem then. So let's go back to our problem. Go ahead and read these two sentences. Can you identify what x bar is, the sample mean is? So hopefully, as you read through that, you said, oh, okay, 182 minutes is the average of the 25 5-year-olds, okay? And so what you got to think of here is that basically the problem has already summarized these results. When I say these results, like it's already summarized x bar for you. It's already summarized s. And so what we've done is that instead of making you calculate the x bar, the average for the 25 5-year-olds, and calculating the standard deviation for them, we've given you those numbers instead of the raw data. That's a lot of calculating that you got to do. And just imagine if we took a sample size of, say, 200 and calculating the x bar there and the sample standard deviation there. Just too long. And so in these problems here, they're going to pretty much be summarized for you. Okay, x bar and s. All right, but this is exactly the same x bar that we calculated back in chapter 2. Nothing's changed there. Okay, it's just that we're just summarizing the results. We're making it easier on you, essentially. All right, recall that the standard error is what? S, the standard error of the sampling distribution of x bar is S divided by the square root of n. So remember, the sample standard deviation, S, is a statistic that varies from what? Sample to sample. And so remember, we have a whole new probability distribution to account for this extra uncertainty. And this new probability distribution is called what? The t distribution. All right. So let's talk about the t distribution. All right. And so the t distribution is bell-shaped and it's symmetric about 0. So if you can imagine that, 0 is in the middle. So that means on the left-hand side, you can get negative values of t and you can get positive values of t. The probabilities depend on degrees of freedom. For the t distribution, degrees of freedom are related to sample size. All right. So when you got to go ahead and figure out something with regards to the t, probably it's going to be related to the sample size in some way, shape, or form. All right, those degrees of freedom. Unlike the standard normal that is unique, there is a different t distribution at every different degree of freedom. So there's a specific distribution at 1 degree of freedom, another one at 2, another one at 3, and they're all called a t-distribution, okay? And they're just slightly different from one another, each one of those. Actually, I'm going to show you a picture here in a little bit that kind of demonstrates that. The t-distribution has thicker tails than the standard normal distribution, i.e. is a little bit more spread out. All right, it's a little bit more spread out. So let me show you a picture here. And so here, I've gone ahead and shown you a t-distribution with degrees of freedom of 2. All right, that's this one here. So notice that this line right here is actually on one that's on top over here. All right, and over here. So you got a little bit more area in the tails. All right, and when you have 6 degrees of freedom, what happens is that the tails shrink a little bit as far as what's there. All right, it's a little bit taller. And then, believe it or not, the standard normal is sitting right here, very close to it. Okay, of 2 degrees of freedom, 6, and just imagine if 30, 50, 100 degrees of freedom. Okay, it's getting closer and closer to the standard normal. All right. So here, the t-distribution gets closer to standard normal as degrees of freedom increase. Okay. And what I told you in the a couple of sections ago, when degrees of freedom is equal to infinity, the t-distribution is equal to the standard normal. So basically what I'm trying to get at here is that what you can think of as the t-distribution as an approximately normal distribution. It's almost normal. All right, you've heard that term before when we talked about the central limit theorem. This is the reason why we called it approximately normal here. All right, it's almost normal. That's the t-distribution. So here is a figure. And let's say that we are creating a 95% confidence interval. And so theoretically what we're doing is we're putting 0.95 as far as the area goes here right in the middle. That means we got 0.025 in this tail. We got 0.025 in this tail. And so if you looked up 6 degrees of freedom, okay, for a 95% confidence interval, I think you would find this value right here, this 2.447. Well, let's go take a look. So we got degrees of freedom of 6 and 95% confidence interval. Let's go take a look. So degrees of freedom of 6, 95% confidence interval. There you go. There's your 2.447. All right. So that's basically what's going on here. Notice that this t table doesn't give you the negatives, and the reason why is because it's exactly the same on the other side because it's perfectly symmetrical. So you got a negative 2.447, and you got the same area here as you do over here. All right. So it'd be kind of redundant to show both. All right. So the last thing, again, I want to stress this, is that a t-distribution is an approximately normal distribution. Okay, that's the last note with regards to the t, or I should call a family of t's. All right, so here's our formula, and x bar would be our point estimate for a confidence interval from u. Critical values coming from the t table. That's why we put t, not z. Standard error. It's this guy right here. All right, and we got to remember our degrees of freedom is n minus 1. Now, like I told you with when we did confidence interval for the population portion P, there's conditions. Okay, there's conditions for every inferential technique. Well, there's conditions here. Let's go through the conditions. One, we either need a random sample or the data comes from an experiment. Remember, experiment is randomized, and so we need some kind of randomization. 2, there are no extreme outliers in the data. All right, there, you know what, when we actually do a problem, I'll talk about that more. And then 3, we need one of the following. Don't need both, we need one or the other. Either we need x to be normal, and that'll be stated in the problem, or 2, we need n to be greater than or equal to, n to be greater than or equal to 30, and the central limit theorem applies. In either case, the sampling distribution will be approximately normal, meaning, i.e., a t-distribution. All right. So the sampling distribution of x bar will be some sort of t-distribution. All right. With what degrees of freedom? N minus 1 degrees of freedom. This is actually step number one in the process of creating the confidence interval. So when we actually get to a problem, you'll see that. Okay, so here's our back to our problem. All right, and needed to create our confidence interval. Remember, it's 90. So the confidence interval here is 90. Okay, and so let's write some stuff down. So x is equal to daily mean screen time for 5-year-old. This is quantitative. Okay, this is quantitative. What's our sample? Well, we had 25, right, 5-year-olds that we went ahead and randomly sampled. So that means n is equal to 25. Degrees of freedom is obviously then 24. If that's our sample, that means our population must be what? All 5-year-old American children. And we already talked about this, that the sample mean x bar will be equal to what? 182. And then what should we label the 28 as? So let me show you up here. It says the daily mean screen time for the 25 children is 182 minutes with a standard deviation of 28 minutes. What symbol are we going to use here? We're going to use sigma. We're going to use S. Well, remember, sigma is the population standard deviation. And this standard deviation looks like it came from a sample, right? And so what do we got here? We got good old S. All right, so the sample standard deviation is equal to 28. What about the critical value? Okay, so we got to remember that we're working with 24 degrees of freedom and a 90% confidence interval. Let's take a look at our t-table. So what was it again? 24, 90, right? 24 and 90. So here's 90. Here is 24. It looks like right here. Our t-table is telling us 1.711 for the critical value. That's what we're going to fill in for the t here. And I have to stress that always got to get that from the t-table or that Excel spreadsheet that I also put in the course. All right. So if you do a homework problem, you don't have the right degrees of freedom on that table, you can look on the Excel spreadsheet that I gave you. All right. Let's go ahead and verify our conditions. So we took a random sample, right? So somewhere here it randomly sampled, right? So we got that check mark. 2, problem does not mention anything about extreme outliers. Now, you could check some sort of plot, right? You can make a box plot. You could go ahead and make a histogram. You can make a dot plot, whatever, okay, stem and leaf. All of those would work probably with this if you had the raw data, right? If you had the raw data, you could go ahead and check it. Probably if you were doing this for real, you would actually go ahead and check the plot, okay? Make sure you don't have any extreme outliers. Here, let's see, the daily screen time for 5-year-olds, that's X in the problem, is normal. Notice that we said that here. Assume that the daily screen time for 5-year-olds is normal. Okay, that was for this last condition. All right, thus the sampling distribution of X bar is what? A t-distribution. It's approximately normal, right? T-distribution. So we have our conditions. Good. Moving on. Here's our formula here. All right, and I filled in the pieces parts. So we got 182 for X bar, plus or minus our critical value. S was 28. Sample size was 25. Be careful not to throw in your degrees of freedom. Okay, don't throw 24 in there. Make sure you throw in 25 N. And then I went ahead and calculated everything out. And I got this down here, 172.42 to 191.58. So what do we think is located in there? If you had to just give it a symbol, what would you say is located in there? We think what? Mu is located somewhere between these two numbers. Doing inferential statistics, right? All right. So last thing we got to do is we got to do the interpretation of the confidence interval. So we're 90% confident that the daily mean screen time for all 5-year-old Americans is between those two numbers that we found with the confidence interval. So notice that it's for all, right? It's not for the 25 5-year-olds. It's for all 5-year-old Americans. Now we have an estimate. All right, we'll do one more. A researcher randomly tests 31 different electric cars. I doubt I probably couldn't even find 31 different models of electric cars, but let's just pretend that there's 31 out there so we can do the problem here. To figure out the average amount of miles all electric cars can travel on a single charge. The average of the 31 cars is 250, standard deviation of 10 miles. Assuming that the number of mile cars can travel is normal, construct a 95% confidence interval for the mean amount of miles all electric cars can travel on a single charge. So what's x? X is equal to the number of miles electric cars can travel, right? That's quantitative. Thus, we're looking at means, not proportions. Sample is 31. That means our degrees of freedom is 30. Population then means all electric cars. Sample mean is x bar, right? 250. Sample standard deviation, 10. It's right there. What was our critical value? Let's see here. N is 31, degrees of freedom of 30. Let's take a look. Oh, let's see here. I got here 2. Oh, that's right. I didn't. I thought, well, maybe this is good for you to go ahead and check this out on the table yourself. But the critical value turns out to be 2.042. All right. So notice that it's just a little bit higher than the value that we would have used if we were using the standard normal. Remember, the standard normal would have been 1.96, but the t is going to make it just a little bit bigger, that critical value. All right, because of that little extra uncertainty that we have, because we're using S here, the sample standard deviation, as part of the formula. So let's verify our conditions. We took a random sample. Problem does not mention anything about extreme outliers, but we could check our plot. Now, the third one, you got your choice here. I did the central limit theorem because since n is equal to 31, that's greater than or equal to 30, the CLT applies, and the sampling distribution of x bar is a t-distribution, right? It's approximately normal. But what else could we have used? I said that x was normal, so you could have even used that. You had both. All right, you had both. I chose to use a CLT because I didn't do it before. All right, I didn't have it in the last problem. All right, so I just rewrote the stuff here, and here's a formula, and I went and plugged everything in. Remember to use 31 down here. That's what I got. So what's our pieces parts here? Remember, this is the point estimate, critical value, standard error is this stuff right here. All right, what would we call that number? The 3.67. That would be the margin of error, right? The margin of error. And so I applied the margin of error. Those are the two numbers I got for the lower and upper bounds of the confidence interval. And what do we think is located in there? What do we think is located in this confidence interval? U, right? The population mean. What's our final step here? We got to do the interpretation. So we are 95% confident that the mean amount of miles all electric cars, right? Not the 31. We know what happened with the sample of 31. Now we are going to apply it to all electric cars can travel on a single charge between the two numbers that we found in our with our confidence interval. Okay? So making a confidence interval from you, make sure you use the t-table, all right, for the critical value. Thank you for your time.